Okay, it's recording already. And all right. Okay, you can see. Okay, so now we begin with 6.3 resistance, reactance, and impedance, but in part D. Explain graphically the dependence of resistance, capacitive reactance XC, inductive reactance XL, and impedance Z on frequency F. Frequency. Who's okay, yes, thank you. If possible, I want to listen to your voice lah, because I cannot check the Google Meet. I'm looking at my slide here. If possible, you talk to me directly. Okay. For the according to relating to the lessons. All right. So okay, and relate dependence of all these value on the frequency and relate it to resonance. Okay, what is actually resonance? Okay, in previous lesson I did talk about resonance. Okay, so okay, let us review back what we have learned about resonance. Resonance is defined as the phenomenon that occurs when the frequency of the applied voltage equal to the frequency of the LRC series circuit. Okay. Okay. Resonant frequency. So basically, resonant at what important here is at resonant frequency, this is what happens. The XC equal to XL. Okay, XC equal to XL. We talked about the phasor diagram before. Okay, let me review back. Where is it? Oh, not this one. Okay. Yeah. So this is the resonant frequency. Okay. In previous lesson, I did talk about resonant frequency already. That happens when the XC equal to XL, they cancel each other. Okay, and then the resistance equal to the impedance. Do you still remember about this lesson? Are you the one who I'm teaching about this resonance? Are you the class?
Yes.
Okay. All right. So okay, let me just write on a new page. Okay. But before we talk about resonance, let us talk about this how this resistance, reactance, and impedance relate on frequency first. Okay. So it is all based on the formula, okay, which you have learned. Okay. So how does this resistance XC, XL, and Z, okay, relate to frequency? Okay, relate to frequency. So for this resistance, it is constant. It is constant. So it is independent of frequency. We can say independent of frequency. That means when frequency changes, resistance still remain constant. The frequency doesn't affect the resistance. Okay. Whereas for XC, the formula is 1 over omega C. Omega is 2 pi F. Okay, correct or not? So that means if for this one, if frequency increase, XC decrease. Okay, XC decrease. So okay, and then for XL, okay, for XL, the formula is omega L, which is 2 pi FL. So for this one, if frequency increase, XL increase. So we can say for these two, they are dependent on frequency. They're dependent on frequency. If frequency changes, these two value will change. Okay. And how about Z? Z, we know that the formula for Z, if let's say in RCL circuit, To find the Z is we need to do all those Pythagoras theorem. We have, you know, let's say XL minus XC square plus R square, isn't it? Is it dependent? Is Z dependent on frequency? Of course, because XL and XC depend on frequency, isn't it? You can see these two they are dependent on frequency. Yeah, they depends on frequency. So we can say Z also depend on frequency. The Z, the impedance also depend on frequency because Z depends on XL and XC. Okay, so only the resistance is independent of frequency. Okay, let us draw a graph. Let me draw a graph to show what happened if you change the frequency and what happened to all these values. So let's say you have okay, this is frequency, and these are the R or XC or XL or Z. Yeah, so the x-axis is frequency, y-axis is the all this value. So okay, first of all I want to draw the graph for R. Graph for R is constant. Okay, if frequency, that means if let's say if frequency increase, okay, so when going from left to right, when frequency increase, what happened to resistance? Resistance remain constant. Understand, class? Resistance doesn't change. This is for resistance. What happened to XC, class? What happened to XC if frequency increase? What happened to XC? Decrease. Yeah, XC, if frequency increase, so that means the XC will decrease. Like this lah. This is for XC. Yeah, XC decrease. What happened if XL, if frequency increase? What happened? They increase, isn't it? Directly proportional. If you can see, XL is directly proportional to frequency, so it is increasing. Okay, understand, class?
Yes.
Yeah.
Yes.
Good. So so what happened to Z? What happened to Z? So Z is you need to combine all three graphs. That means what you need to do is let's say I take a point. Yeah, to get the graph of Z, you take a, let's say I take a point of, let's say this point. I take this point. Okay, I take this point. So what do you think? When XL and XC cross this point, that means at this point they are same value, isn't it? At this point, the XL equal to XC, isn't it? At this point, at the black point here, XL and XC at certain frequency. In fact, this is the resonant frequency. This is the what we call resonant. Just want to throw off this one. Okay, so in fact at this point, this is called the resonant frequency. What happened when resonant frequency the XL equal to XC? Because you see they all have they cross the same point, so XL equal to XC value over this point. So what happened? So let's find out what's the value of Z over there. Let's find out what's the value of Z over there. So at this, when frequency equal to resonant frequency, we can say okay, Z equal to XL minus XC square plus R square. So they are equal value, so they cancel each other. So they only left with what? So only have square root of r square, which is z is r. Yeah, understand? So the impedance is equal to r. So that is a point for z. Yeah, the point for z. Okay. That is the a point for z. Now I want to plot. Actually, I want to plot a graph of z. Okay. So what happened if before? Let's say before the resonant frequency. What happened before resonant frequency? The x can see xc is bigger than xl, isn't it? If over here, okay, I want to write something. So over here, the xc is bigger than xl. Yeah, before here, and after that is all xl bigger than xc. Correct, not class? Yeah, correct lah. I should. I think xc bigger than xl. Now this one xc smaller than xl. Okay, so no matter what, before and after, okay, before and after, what I can say is so they are not equal. That means when they minus, when the xl minus xc, when because they are not equal, okay, one of it will be bigger. Okay, so when you square it, of course, more the value more than 0 lah. There be certain value come up from here, and then plus r square. R is always constant all the time. So the graph of what I can say, the graph of z. In fact, the graph of z. Actually, this is the point. Yeah. At resonant frequency, the z is r, isn't it? So actually, this is the graph of z over here. Graph of z over here, because z equal to r, impedance equal to r at that point. So before that is all how to say, more than r lah. Yeah, before that is more than r, because this cannot be 0 value. Yeah, so it's more than r. So yeah, the graph is something like, something like, if I'm not mistaken, is something like this. Is it correct? Yeah, it's like this. See, at resonant frequency, the z equal to r. You see that? Okay, so that's the graph of z. So z is lowest when during what frequency? When during resonant frequency. Okay, z is at the, I can say it is at the minimum. Understand? It is at the minimum, because at resonant frequency xl equal to xc. So they cancel totally. So just left with r. So z is at the minimum. Okay, so the graph of z is at the minimum. So before that, before resonant frequency and after resonant frequency, there'll be certain value over here. Yeah, xl minus xc must be a certain value from over here. So definitely z is always bigger than r. Yeah, z is always bigger than r. You understand what I'm talking about, class?
Yes, sir.
Yeah. So so I can say z is dependent on frequency, because why? Because of xl and xc. Yeah, z depend on xl and xc, and xl and xc both depend on frequency. So in the end, z depend on frequency also. So only one thing is independent of frequency, that is resistor, independent of frequency. Okay. All right. Now I want to further talk about the resonant frequency. Okay. So when frequency equal to resonant frequency, Fr. Okay. So the most important thing is XL equal to XC. Okay, XL equal to XC. So okay, let us draw a phasor diagram Okay, so this is the now I'm talking about resonant frequency, resonant frequency, which is this lah. Okay, so when resonant frequency happen, XL equal to XC. So let's draw the phasor diagram. Let's draw the phasor diagram. So need more space. Okay, the phasor diagram. Actually, I thought to I teach you about this. Now I teach you again. Yeah. So current. This is the resistance, and XC XL equal value. XL XC equal value. They are equal value. Okay, so they cancel each other totally. So just left with R. So the R become the Z, which is at the minimum. So yeah, hold on a second. Okay, so now continue recording. So Z is at the minimum when resonant frequency, when resonant frequency, Z is at the minimum. So this is the graph lah. This is the graph. Okay, so okay, XL equal to XC. XL, what's the formula for XL? Formula for XL is omega L, and XC is 1 over omega C. Okay. Now this happen when 2 pi f. Omega is 2 pi f, but XL equal to XC when this frequency is FR, resonant frequency. Okay. And then this is 1 over 2 pi FC. This resonant frequency lah. Okay, when resonant frequency, the XL equal to XC. Okay, so so FR square, and then here you get 4 pi square. Yeah, these 2 pi go below, and then LC go below. Yeah, so we square both sides, square root both sides, we get 1 over. So when square root the whole thing, when I square root both sides, so this 4 pi square become what? Become 2 pi. I become 2 pi and then square root LC. Understand, class? Okay. So this is the formula for resonant frequency. This is the formula for resonant frequency. Okay, you can calculate the resonant frequency using this formula, 1 over 2 pi square root LC. Okay. One more thing is okay. Now based on the formula, V source equal to V source is Iz, isn't it, class? Okay, V source equal to V source, because we have what? We have VR equal to IR, we have VC equal to IXC, we have VL equal to IXL. So if V source equal to IZ, because if impedance correspond to V source, if XL correspond to VL. Understand this one, class?
Yes, sir.
Okay, good. So now, at resonant frequency, okay, at resonant frequency, when frequency equal to resonant frequency, XL equal to XC, Z is at the minimum. See that? Z is at the minimum. Z is at the minimum. Because why minimum? Because it only has R. XL and XC, there are no balance and they totally cancel each other. No more XL and XC, just R. So Z is at the minimum. You see the graph? The Z is at the minimum. Okay, the Z equal to R at this point. You see that? Z equal to R at this point. So Z is at the minimum. So we can say the current is the maximum. At this point, the current is at the maximum. Do you see that, class? Current is at the maximum. So I can say this current has a maximum value, is at the maximum value. Okay. So when Z is at the minimum, current is at the maximum. So at other point, let's say at other frequency than resonant frequency, the current is actually smaller. Current is actually smaller because Z is higher. The impedance is higher. But at the resonant frequency, the Z is at the minimum. So current is at the maximum. Okay. Another thing is, if you look at the phasor diagram, okay, where is the phi? You can't see any phi, right? What is the phase angle? I want to talk about the phase angle. Okay. In fact, you know, this graph can be translate. This graph translate to the same thing also. Okay, so this XL is actually VL lah. I can say it is VL over here. So this is VC and this is what? VR. Understand? And this Z minimum means it is this is the V source. Yeah, V source. No. Yeah. So that means the V source is only V equal to VR. Huh? When Z is R, so V source also equal to VR. So what can you say about the phi here? Because the phase angle is between V source and current, isn't it, class? You remember about phase angle? Phase angle is always between V source and current. So now the phase angle is 0. The phase angle is 0. Okay, is 0. So what can we say about? So let's calculate the power factor. Okay, what is power factor again, class? Cos phi. So which is cos 0. Cos 0. So it is equal to cos 0 equal to 1. Okay, cos 0 equal to 1. All these are important characteristic of resonance. Resonance. Okay. So if you yeah lah. What else? Did I miss out? Did I miss anything? No, but I have more things. I explain more than that. Yeah, I explain more than that. Yeah. So okay. So again, I want to summarize. So when resonance, what can you say about resonance? Yeah, what can you say about resonance? You can say XL equal to XC. You can say you know, the Z is at the minimum, which is equal to R. The power factor, which is cos phi equal to 1. In fact, I can say one more thing. When phi equal to 0, that means if you look at this diagram, the V source is in phase with current. So no one is the boss. That means they travel together. Current and V source, they travel together. They are in phase. Okay. So that means I can the phi is 0 degree. Do you understand what is mean by phi 0 degree? That means the V source in phase with current. In phase, they become maximum together, they become 0 together in phase. no one leading. Okay, yeah. Besides that, I want to add when Z is minimum, the current at this time is maximum. Okay, and when XL equal to XC, so you get this formula, frequency is equal to 1 over 2 pi. So this is the thing lah. Okay, class. Now, okay, I finished about resonant. Yeah, the source frequency is in phase with current. Okay, now I want to talk about the next part, which is power and power factor 6.4. Yeah. So let's calculate. We need to learn about how to calculate the average power, instantaneous power, and also power factor. Cos phi. Okay. So let us first look at average power and instantaneous power. Okay. So also refer to these three things lah. Pure resistor, we go one by one. Pure resistor, pure capacitor, and pure inductor. Okay, we go one by one. Pure resistor. So, oops. Okay. All right. Let's move on. New sheet. Let us talk about power first. Yeah. Let us talk about power. So power, we have two things. We want to look in two things. We want to look at we want to calculate the average power, and we also want to calculate the instantaneous power. Okay. So power average and power instantaneous. So now let us first focus on pure resistor. Okay, pure resistor circuit, that means only have one. In fact, actually, let me see. Did I? No, this is where did I? No. This is all history. Yeah, history. Okay. Oh, I did. Here. Yeah, pure. Yeah, this one. Better I continue from here. Okay. This is the previous lesson I give to another class lah. I Google Meet and I teach in here. Yeah, in OneNote. Okay. For your class, I teach in the face-to-face class. Yeah. Okay. So I will continue the power from here. So last time we just talked about current and voltage, how they changes sinusoidally. Yeah, we learn about what for pure resistor, voltage in phase with current, and then pure capacitor is ICE, and then pure inductor is LE. Still remember that, class? So for pure capacitor is current leading, pure inductor is voltage leading. But for resistor is voltage in phase with current. Okay, so I want to continue from straight away from here. Okay, so as I said, power, we look at two things. We look at the average power and instantaneous power. So for pure resistor, what is the formula, class? I equal to I naught sine, and then V equal to V naught sine. Yeah, right. Okay, I want to make it simple. Better if I. Okay lah, never mind. I don't want to. Okay, for pure resistor. Okay, I just want to tell you that it's related to the previous part. So for pure resistor, okay, again, there are current in phase with the voltage VR. Okay, they are in phase. So when in phase, that means what formula, class? Okay, that means the diagram is like this. Okay, this is the current, and this is the voltage R, okay, rotation anti-clockwise. Okay, so the current formula is both are sine graph, correct not class? And then VR is also sine, V naught R sine omega t. Okay, so now to calculate, first we calculate instantaneous power. Yeah, instantaneous power. Okay, what's the formula for instantaneous power? Okay, I want to talk about, so I put it here, power instantaneous power. Okay, instantaneous power. Okay, never mind. Put it power instant equal to instantaneous power is you just multiply lah, I multiply VR. Understand? I multiply VR. So what do you have? So just multiply the formula, I naught sine omega t multiply with V naught R sine omega t. I naught sine omega t multiply by V naught R sine omega t. So in the end you get V naught multiply I naught multiply V naught R, here becomes sine square omega t. That's the formula for instantaneous power. Instantaneous power. So I naught multiply V naught R, so you get what? You get, this is the P naught. Then peak current multiply peak voltage, so you get the peak power lah, maximum power. Sine square omega t. So what is the graph for instantaneous power, class? What's the graph? What's the graph for instantaneous power? So you get okay, you see sine square omega t graph. This is a sine square. It's a sine square graph. So is there any negative value? Because sine, the maximum value is 1, isn't it, class? Okay, okay, class, I ask you, mathematics, for sine equation, the value is between 1 and -1, correct or not, class? Correct or not?
Yes.
So the minimum is -1, maximum is 1. But if sine square, what's the minimum? -1 square also get +1, correct or not? So the minimum is 0. Yeah, there's no -1. Whatever negative value all get square already, so become +1. Okay, so what I can say is for instantaneous power, yeah, for instantaneous power, the maximum is P naught. So I can say if P naught, if the sine square omega t, it is the maximum is, if sine square omega t is value is 1, that means the instantaneous power is P naught. Yeah, P naught multiply 1, you get P naught lah. If multiply 0, you get 0. Correct or not, class? So the graph is what? What's the graph? Power versus time. Do you have negative value? Does the graph have negative value?
No.
No,
No.
it only has positive value, and power is the maximum is P naught lah. Because sine square omega t, the maximum can be only 1. It cannot go to 2 or what. So the maximum is still P naught. The maximum is still P naught. And then minimum is 0. Minimum is 0. Okay, and it doesn't have negative value. Okay, so the graph is over here only. So it's sinusoidal graph on top of the x-axis. So this is the graph. Okay, this so the graph is like this lah. Not lousy graph. I mean my drawing is lousy. Very lousy. Yeah. Okay. Enough lah. Okay. So the graph doesn't have a negative value because sine square what? Okay. So this is the instantaneous power. Instantaneous power. Okay, now I want to find average power. Average power means the middle line lah. The middle line. So that's the average power. Understand? That's the average power. So what's the average power? Average power is half P naught. Half P naught. Okay. In fact, this is half P naught. Okay, class.
Okay, sir.
A lot of information today I teach. Okay. In fact, everything is in the notes. Here I just I just like to write. Yeah, sometimes you learn it better when I show it. Okay, so it is half P naught. Okay, so now I want you to put in the value I naught V naught R. Okay, P naught actually is, okay, what is P naught? P naught is actually I naught V naught R. You agree or not, class, just now? So P naught is I naught V naught R. So I naught V naught R. Okay, I naught V naught R. So in fact, still remember about the equation, how to calculate the RMS value. IRMS equal to I naught over cert2, correct or not? So V naught R also is V RMS R over what is it? V RMS R is V naught R over cert2, correct or not, class? Divide by cert2, you get V RMS value kan? So that means this, if you look carefully, this is I naught V naught R over 2, right? Actually this is this is actually I RMS multiply V RMS R. Correct or not, class? You see, IRMS is I naught over cert2 multiplied by, correct? IRMS is I naught over cert2. VRMS R is V naught R over cert2. So when I multiply these two together, cert2 multiply cert2, you get 2. Correct? Paham kah?
Yes, sir.
Cert2 multiply cert2, you get 2. So what conclusion can you make? From the graph, you can see the average power for a pure resistor circuit is half P naught. Half P naught, that's the average power. So average power, actually you can calculate. So the conclusion you can make is the average power equal to the root mean square value multiplied together. That's why root mean square value is so important. That's the conclusion we can make. So the average power is, to get the average value, we always take the root mean square value to multiply. We take the root mean square value to multiply. That's why my project in Arduino, I try to find the root mean square current to get the power consumption of electrical appliance. Root mean square current, root mean square value. That is, the root mean square value is to find the power. Understand? That is also the meaning. That is also the definition for root mean square value. Remember? Remember the definition of alternating current? No, I mean the root mean square value. Root mean square current. Root mean square current is the steady direct current DC which produces the same power, which is the average power produced by the AC? Average power. Average power. Do you see that? We use the what value? Root mean square value to get the average power. The root mean square value is a useful average value specifically to calculate the average power consumption by any electrical device. Okay, this my fridge use have few hundred watt of power. My iron use 1,100 watt of power. All that calculated using root mean square current value and root mean square voltage value. Okay, proven by all the equations. You see that from the graph, I get the average power, and that is from here I get the root mean square value multiplied together to get the average power. Okay, class. So this one is power dissipated. Now I want to talk about pure capacitor. Okay, following is pure capacitor. Do you still have the patience with me? So for capacitor is I's. Okay, who's the boss? The current, right? So for this one, current leads voltage C by 90 degree. So what I can say is from the graph I can see that okay, from the graph, okay, let me use them. Okay, from the graph, let's say if my current, okay, this one I put like this lah. Current is the boss. Rotation anti-clockwise. I put current as the cos. So current at the front, current is the boss. So VC lagging behind 90 degree. VC is over here. Correct not, class? 90 degree.
Yes.
Current is the boss at the front. Current is the boss. Rotation anti-clockwise. Okay, so what equation is current? I naught cos omega t. How about VC? Voltage? V naught C sine omega t. Is a sine equation, correct not, class? So how to calculate the average power? No, instantaneous power first. Yeah, first we look up about instantaneous power. Okay, instantaneous power. So instantaneous power is we just multiply lah, okay, instantaneous power. Use your mathematic prowess, yeah, use your mathematic talent. So IVC, like just now is IVR, now IVC because pure capacitor. So multiply these two, you know, physics cannot be separated by mathematics. So this is a V naught C sine omega t. So in the end, I get I naught V naught C. So this is what? Sine omega t cos omega t. My God, I have sine cos. So how to do? Remember what you learned in your Ed Maths. What grade do you get for Ed Maths? A minus, B or D or C or D. Ed Maths in your high school. Mathematic tambahan. Sin theta, this is called the trigon identity. Sin theta, cos theta. Remember 2 sin theta cos theta equal to sin 2 theta. Remember this one? Familiar?
Yes, familiar, sir.
This is what we call identity. Trigonometry identity. Identity. So 2 sin theta cos theta is sin 2 theta. Now we are using what? Sin omega t cos omega t, and then this is sin 2 omega t. So that means sin omega t cos omega t is equal to sin 2 omega t divided by 2. Okay? Divided by 2. Yeah. So this is I naught. Okay, in fact, this is I can say P naught lah. I naught, V naught is P naught. Yeah, and then this whole thing This whole thing is what? Sine 2 omega t over 2. Understand? That is sine 2 omega t over 2. So I get what? What I get? What do I get? So I get what do I get? Half P naught sine 2 omega t. That is the instantaneous power. Now can you draw a graph for this one? Can you draw a graph? In fact, I rewrite the formula. Actually, it's just very simple formula. It's P naught sine 2 theta only. Understand? So you can actually regard this sine 2 theta is what? It's like a normal sine theta equation. A normal sine equation. That means it can have what? It can have one. It can have what? 1 and negative 1. Correct or not, class?
Yeah.
Can have 1 and negative 1. So it's just like a normal sine. Just the graph will be a little bit narrower lah. Yeah, but it's still maximum 1, minimum negative 1. It can go to negative 1. It got negative value. Just now is the equation is sine square. Sine square don't have negative value. It got 0. The minimum is 0. This one is sine square for pure resistor, sine square. This one doesn't have sine square. It's just sine 2 theta. It doesn't have sine square. So this one got negative value. It can go to positive 1 and negative 1. And then the maximum is what? The amplitude is half P naught. See that? It can go to 1 and negative 1, but the maximum is okay. What do I want to do? I want to draw the graph for instantaneous power. So the maximum is half P naught. Agree? Half P naught, and then negative 0, and then negative half P naught. Because when sine 2 theta equal to 1 is half P naught. When sine 2 theta equal to negative 1, it becomes negative half P naught. The instantaneous power. So it's still a sine equation, normal sine equation. Sine 2 theta is just like sine theta. It's still like a sine equation. That changes according to like this. Just a normal sine equation. Understand? Simple, right? Okay. So from here, this is the instantaneous power lah. This is the instantaneous power graph. Now, what is the average power? What is the average power? Average power is over here. I should use average power is the middle line. So for this one, the average power is 0 watt. Okay, is 0 watt. That means what? Capacitor, the average power is 0. What does it mean? What does it mean? Just now this one, power average is this one. Yeah. Okay. You have a certain value. Yeah. Power average. But this average power for capacitor is 0. Okay, so I just want to highlight. I just want to highlight this. Okay, for resistor you have power average, but for capacitor is 0 power. Average power is 0. Yes, and the middle line. Remember the middle line. This one, the middle line is over here. Resistor middle line is over here, but for capacitor is 0. Now, okay, let's look at inductor. Let's look at inductor. They'll be the same. Yeah, inductor will be a little bit quicker. I won't stop too much. So again, this one is LE, and then this one is is voltage leading. Voltage is the boss now. Voltage leads. current by 90 degree, and then the graph is, voltage is the boss, current is lagging behind, so voltage is the boss. So the equation is the current is sine, the voltage of inductor is V naught L cos omega t. Correct not, class? Voltage is cos, current is sine, correct? In the end, you see, let's calculate the instantaneous power. Instantaneous power is IVL. Yeah, just now is IVC, now is IVL. So you get current is what? I naught sine omega t. VL is V naught L cos omega t, correct? In the end, you see, class, you get the same like capacitor. I naught V naught L sine omega t, this one cos omega t. Do you see something familiar here, class? Is it the same like capacitor? Is it the same like capacitor? If
Yes,
capacitor is I naught V naught C sine omega t cos omega t, this one also I naught V naught L sine omega t cos omega t, because both of them, one of it is cos omega t and sine omega t. This one is sine omega t cos omega t. It's the same. You see? They get the same. So what I can say is I can just copy this part. I can just copy and paste here. So it's the same for this one, and also the graph, and the average power also 0. Yeah. Okay. It's same graph like the capacitor. Yeah. So this one goes elsewhere. Okay, goes here. Yeah. So you see, it's the same. Yeah. Okay. I know it's time's up, but 1 minute more. Yeah, just 1 minute. Give me another 1 minute. So the why, now the question is why pure resistor has power I RMS V RMS R, but for capacitor and inductor both average power is 0. Why, class? Why? Look at the circuit. This is resistor, pure resistor. And then you also have the other pure capacitor, and then you have the pure inductor. Pure inductor. So L. Okay. Now, resistor use up power. My kettle, my iron generate heat, isn't it? Got power dissipated. So the power average is power used or dissipated. So my resistor actually use up power. It use up power. So to calculate how much power or power consumption, which is equal to I RMS V RMS R. Understand? Power use. But for capacitor and inductor, they does not use any power. The power average of power use is 0. That means what? That means they can store power, they can return power. Because we know that capacitor can store energy. Because they have ability to store energy and return energy. Understand? They can return energy. Inductor also store energy and return energy. How capacitor store energy? Is stored in the form of electric field, charging, discharging. Remember that? Storing, charging, discharging. They store in the form of electric field, and then they can discharge. When they discharge, they return energy. So in the end, when charging, discharging, they does not use up any power. So power is continuously store and return. The average power, no power consumed, no power dissipated, no power dissipated, no power loss, no power loss or no power dissipated, no power used. Same goes to inductor, same goes to the solenoid. It can store in the form of magnetic field. It can store and return also. It can store and return energy. Yeah, with the cycle. Like this one, is like you see positive means store energy and then return energy. Store energy, return energy. This one also store energy, return energy, store energy, return energy. So in the end, for capacitor, inductor, they continuously store and return energy to the source. So over time, the power average of for both of them is 0. No power loss, no power dissipated. Yeah. But for resistor, they cannot store power. Resistor cannot store power or cannot store energy. They just use energy. They cannot store energy. They just use energy. Okay, so that's all for today's lesson. Yeah, I'm sorry for rambling so much. So I hope that you anything can understand the class. Yeah.
Yes,
Cla-
sir.
can you understand the class? So capacitor and inductor, they does not use energy, so average power is 0. All right, but for resistor, they cannot store energy, so they can use energy. Yeah. So the formula to calculate how much power consumption is just take the root mean square current multiply root mean square voltage. Okay. And that's all for today's lesson. Okay, hope you understand. Okay, see you in the next class. Bye.